All right, boys and girls. Today I want to talk very briefly about beta decay. Grab the notes that I asked you to print out from the other day. There are notes on alpha, beta, and gamma decay, and jump to page 4, where it says beta decay. All right, we're going to go over beta negative decay today. There's also a beta positive. We'll get to that, but not today. Beta negative decay. Now, this is a type of radioactive decay. A nucleus will undergo radioactive decay when the number of protons and neutrons in the nucleus isn't quite right. There's a problem with the ratio of protons to neutrons. I don't want to get into a big discussion of that, but that's why these nuclear changes occur. All right, so in a parent nucleus, right, I have a certain number of protons. I'll use P plus for protons, and a certain number of neutrons. And it turns out that this ratio of protons to neutrons there's something wrong with it. All right. I'm not going to go into the details about that, but we can make this unstable nucleus a little more stable by undergoing beta negative decay. And what is beta negative decay? Listen to this. One of the neutrons within the nucleus, right? Let's say this is my neutron right here, actually undergoes a change in which the proton or the neutron becomes a proton plus an electron. So my little neutron here does some voodoo magic and becomes a proton. Now that proton remains in the nucleus. So really what happens is that the neutron number goes down 1 and the proton number goes up 1 during this change. And the other piece of this transformation, the electron goes shooting out of the nucleus. And this electron, which is shooting out of the nucleus because of this change, is what we call our beta particle. And I think you can see why we call it beta negative particle, because electrons have a negative charge, beta negative. Okay, so that is, in essence, all we need to know in order to do this. All right. Let's take a look at the first example here. It's actually labeled example number 3. Say I have a calcium nucleus. Now calcium has 20 protons in the nucleus and a total mass number of 46. And this is going to undergo beta negative decay. All right. So let's think about what we just talked about. All right. I have 20 protons in the nucleus along with 26 neutrons. All right. The 20 and 26 add up for 46. Now when beta negative decay happens, one of the 26 neutrons is changed into a proton. So we cut down our neutrons from 26 to 25, and the proton count goes from 20 to 21. As we can see that the total number of particles in the nucleus remains constant. So whatever is produced as a result of this beta decay, its total mass number is still 46. Right? But what is the case is that the proton count went from 20 to 21. Now, what element is element number 21? It is scandium. So we're going to have to write scandium as the product here. And the beta particle. How do we write a symbol for a beta particle? Well, we could use the Greek letter beta to symbolize that. But what are the numbers that we put here? If we think about it, the numbers here represent the number of protons, but it also represents the number of positive charges in each of these nucleus. It has some relationship to the charge of the particle we're talking about. This original calcium nucleus had a charge of plus 20 in the nucleus. Right? So if we think about this bottom number as having to do with charge, we could simply say that the beta particle has a -1 charge because it's an electron. All right. And the top number has to do with mass. Well, how much mass does an electron have? We discussed this a long time ago. An electron has nearly no mass, so small in fact that we, for all intent purposes, take it to equal 0. Okay. Now, just like alpha decay, we can do a quick little check here. We use the yield sign here as almost an equal sign in an equation. Something on the left side of the yield sign equals something on the right side of the yield sign. What is the total bottom number on the left side? It's 20. What's the total of the bottom numbers on the right side? 21 and a -1 make a total of 20. Okay, so they're conserved there. Same thing with the masses. The total mass on the left is 46. Total mass on the right is 46. So that's one way of checking this. So calcium-46 undergoes beta decay, producing scandium-46 as the daughter, along with our beta particle. When we're considering beta decay, we have something else we need to discuss very briefly. If we go to page 4 to page 5 on this notes, right here at the top, there is only one other thing we should put in our reactions for beta negative decay. When physicists first examined beta negative decays, they figured that since the electrons that are the beta particles are so light, they should just go shooting out of the nucleus at tremendous speeds. In reality, however, a lot of them moved very slowly. In order to conserve momentum, there's a law in physics called the law of conservation of momentum, it was realized that a very small neutral particle must also be emitted during this beta decay. And today we call this this particle that accounts for some of the momentum of this process is called an antineutrino, and give it the symbol, and it looks like a V, and we put a bar over it to designate it as the antineutrino. We're going to see with the beta positive decay that we get a regular neutrino, not an antineutrino. Don't get all concerned about antineutrinos and neutrinos and anything else. All I want to do here is, for the sake of completion, saying that when we undergo a beta decay, that there's something else produced. It has no charge, it has no mass, but it does carry away some of the energy of the process, and that just makes everything copacetic for the physicists, that they're conserving energy and they're conserving momentum by stating that there's another particle coming out of this beta emission. And there, I think we are done with our little discussion of beta emission. Let's just go through and do a couple more examples of a beta negative emission. Let's say that we wanted the complete beta negative decay reaction for, and let's just say zinc with a mass of 66. Okay. Now, if that's all the information I gave you, you'd have to start assembling this reaction equation on your own. All right, I need the bottom number here for zinc. How many protons does zinc have in its nucleus? Now, when I look at the periodic table, zinc is atomic number 30, so it'll be 30. All right. This is the parent nucleus. All right. Something internally is happening to this zinc nucleus, the end result of which is the emission of a beta negative particle. Right? Once the beta negative particle is emitted, I end up with some new daughter nucleus. Right, what is this daughter nucleus? Well, we have to go back and recognize what we discussed in the previous problem, that a neutron inside this nucleus undergoes a change and becomes a proton plus an electron plus an antineutrino. Let's not forget that. One of the neutrons in this nucleus is now gone. It changes into a proton, which remains in this nucleus. So there we go. That's our first thing here, that our zinc with 30 protons becomes something new with 31 protons. That's this guy. What is 31 protons? Well, we look on our periodic table. 31 is gallium, so we can put a Ga right there. All right. All right, plus my beta particle. This is my beta particle, which is really just an electron. I write that into my equation this way. All right, beta is always going to be that. Plus my antineutrino. Now this has no charge and no mass, so there's a 0 and a 0 there if you want to keep track of the numbers. The only issue, or the only other bit I have to concern myself with is, what is the mass of, or the mass number of this daughter nucleus? Well, the total mass number on the left side of the equation is 66, so the total mass number on this side is 66. The beta contains no mass, the antineutrino contains no mass, so all of it's got to be here on the gallium, so that's going to be gallium 66. All right, so there we go. That is the complete beta negative decay reaction for zinc 66. And let's do it the other way around. Let's say I have some unknown nucleus which undergoes beta negative decay. I'll know that because I'll see something like this in the equation. I'll see this, that's beta, and it's a -1, so it's negative beta, and an antineutrino. Right? And let's come up with something here. Let's say it's nitrogen with a mass of, let's say, 16. All right. Now, if you look on your periodic table, nitrogen has atomic number of 7, so this would have to be 7 here. So this is my daughter nucleus. This is my beta negative particle. This is what would be considered my radioactive emission, and my antineutrino. Right. What would produce this mess? What do I have to start with? What is my parent nucleus? Right. Now again, we could figure this out pretty simply by just using all these bottom numbers. 7, -1, and 0 make what? Add them all together and you get 6. Right? The parent nucleus must have 6 protons in its nucleus. Right? It's the only way these numbers work out. And element number 6 is carbon, so that has to be C. Okay? Same thing with the top number here. This mass number here has to be exactly equal to the sum of the mass numbers on the other side. Well, the antineutrino and the beta particle contain no mass. The only mass is right here from the nitrogen. It's 16, so that must be the mass of the parent nucleus. So there we go. You have another properly formed beta negative decay.